After studying this module, you shall be able to know about nature of linear MCO linkage, learn how the molecular orbital theory applied to carbonyl, analyze the different modes of attachment of carbonyl to the metal ion. Let us see the Lewis formula for carbonyl. Carbon atom has 4 valence electrons while oxygen atom has 6 valence electrons. According to their atomic number, electronic configuration for carbon is 2,4 and for oxygen is 2,6. Carbon and oxygen atom share 3 electron pairs between them to complete the octet, leading to the formation of triple bond. Both carbon and oxygen atoms complete the octet of electrons in their valence shells. In 2 bond pairs, carbon and oxygen atoms provide 1 electron each and thus 2 normal covalent bonds results. In the 3rd bond pair, both the electrons are provided by the oxygen atom and thus it leads to the formation of coordinate bond. Both carbon and oxygen atoms of carbon monoxide molecule have 1 lone pair of electrons. Now we see the hybridization approach of carbonyl. Both carbon and oxygen atoms of carbonyl molecule are sp hybridized. Valence shell electronic configuration of carbon atom is 2s2 2p2 and valence shell electronic configuration of oxygen atom is 2s2 2p4. The singly occupied spz hybrid orbital of carbon atom overlaps with the singly occupied spz hybrid orbital of oxygen atom in the linear fashion, forming a sigma bond. You can see from the diagram the singly occupied 2px atomic orbital of carbon atom overlaps with the singly occupied 2px atomic orbital of oxygen atom in sidewise manner, forming a pi bond. The filled 2py atomic orbital of oxygen atom overlaps with the vacant 2py atomic orbital of carbon atom in sidewise manner, forming a oxygen-carbon coordinate bond, which is also a pi bond. According to this concept, there are 3 covalent bonds between carbon and oxygen atoms in carbonyl molecule, and both the carbon and oxygen atoms have lone pair of electrons in sp-z hybrid orbitals. Let us see the molecular orbital theory. The molecular orbital theory was put forward by Hunt and Millikan in order to explain the nature of covalent bond. The main points of this theory are: first, the molecular orbitals are produced by the linear combination of atomic orbitals of the comparable energies lying on 2 or more different atoms. They may be different or they may be same. The atomic orbitals taking part in linear combination should have the similar symmetry property about the internuclear axis. Third, the number of molecular orbitals produced is always equal to the number of atomic orbitals taking part in linear combination. Fourth, if the 2 atomic orbitals take part in linear combination, 2 molecular orbitals are produced. One of these molecular orbitals has lower energy than both the atomic orbitals. It is called bonding molecular orbital. The other molecular orbital, which has higher energy than both the atomic orbital, is called antibonding molecular orbital. Now from this diagram we can see that the atomic orbital of atom X and atomic orbital of atom Y combine to form the molecular orbital of molecule XY. The bonding orbital is termed as xi b, whereas the antibonding orbital is termed as xi a. Bonding molecular orbital is formed by the addition of atomic orbitals, while the antibonding molecular orbital is formed by the subtraction overlap of atomic orbitals. Xi bonding is the combination of xi x plus xi y, whereas the xi antibonding is the subtraction overlap of xi x minus xi y. If both the atomic orbitals have the same energy, they contribute equally to the bonding and antibonding molecular orbitals. If one of the atomic orbitals has lower energy than the other, it will contribute more to the bonding molecular orbital. The xi bonding is equal to x, which is the coefficient of x atomic orbital, into the wave function of x atomic orbital plus the coefficient of y atomic orbital into the wave function of y atomic orbital. If y is greater than x, that means if y is more electronegative than x. Conversely, more stable atomic orbital contributes less to the antibonding molecular orbital. Xi antibonding is equals to x, which is the coefficient of x atomic orbital into the wave function of x atomic orbital minus y, which is the coefficient of y atomic orbital into the wave function of y atomic orbital. Next, Aufbau principle, Hund's rule and Pauli's exclusion principle are applicable to the molecular orbitals also. Next, if an electron enters bonding molecular orbital, the electron density between two nuclei increases. It increases the attractive force between two atoms and decreases the energy of the system. On the other hand, when an electron enters antibonding molecular orbital, the electron density between two nuclei decreases. It increases the repulsive force between two atoms and increases the energy of the system. Each electron pair of the bonding molecular orbital constitutes one covalent bond, while each electron pair of antibonding molecular orbital cancels one covalent bond. The bond order, that is, the number of bonds in a molecule, is given by the formula which states that the number of electrons in bonding molecular orbital minus the number of electrons in antibonding orbitals divided by 2. Next, any molecule is stable only when the bond order is either equal to or greater than 1. If the bond order is equals to 0, the molecule does not exist. If the bond order is between 0 to 1, the molecule is unstable. Let us understand the molecular orbital theory for a carbonyl molecule. Oxygen atom is more electronegative and smaller in size than carbon atom. Therefore, the orbital of oxygen atom have lower energy than corresponding orbital of carbon atom. The sp-Z hybridization takes place on both carbon and oxygen atoms. Two hybrid orbital of carbon or oxygen atoms are not identical. The lower energy sp-Z hybrid orbital has greater S character and is more electronegative, while the higher energy sp-Z hybrid orbital has greater P character and is less electronegative. The lower sp-Z hybrid orbital of carbon atom is comparable in energy with the high energy sp-Z hybrid orbital of oxygen atom, and they combine together forming bonding sigma and antibonding sigma star molecular orbital. The very low energy sp-Z hybrid orbital of oxygen atom and the high energy sp-Z of carbon atom are far apart in energy and they remain non-bonding, and they are localized on oxygen and carbon atoms respectively. These hybrid orbitals are occupied by lone pair of electrons and are directed away from carbonyl bond. The bond order, that is, the number of bonds in carbonyl molecule, is given by the bond order formula, that is, the number of electrons in bonding orbital minus number of electrons in antibonding orbital divided by 2. So we have 6 minus 0 divide by 2 as 3. Let us now see the molecular orbital diagram for carbonyl molecule. It is being characterized into 4 categories. 1 is the atomic orbital of carbon atom before hybridization. 2. The atomic orbitals or hybrid orbitals of carbon atom after hybridization. 3. Atomic orbitals or hybrid orbital of oxygen atom after hybridization. And 4. Atomic orbital of oxygen atom before hybridization. The 2px atomic orbital of carbon atom and the 2px atomic orbital of oxygen atom take part in linear combination forming bonding pi 2px and antibonding pi 2px star molecular orbitals. Similarly, the 2py atomic orbital of carbon atom and the 2py atomic orbital of oxygen atom take part in linear combination forming bonding pi 2py and antibonding pi 2py star molecular orbital. The sigma bonding and pi bonding molecular orbitals are polarized towards more electronegative oxygen atom, while the antibonding pi star molecular orbitals are polarized towards less electronegative carbon atom. You can see from this diagram the sigma bonding molecular orbital, the pi bonding molecular orbital and pi star antibonding molecular orbital. The molecular parameters of carbonyl molecules are bond order equals to 3, bond length equals to 1.131 angstrom, bond energy equals to 1072 kilojoules per mole, magnetic property is diamagnetic, IR absorption peak at 2143 cm inverse. According to the molecular orbital theory, the carbon monoxide molecule can be represented as this, where we can see that the molecular orbital on carbon is p character rich orbital, which is less electronegative and more directional, whereas on oxygen it is rich in s character, it is more electronegative and less directional. Let us now see the nature of bonding in linear MCO linkage. Carbonyl molecule is an ambidentate ligand. It has lone pair of electrons on both carbon and oxygen atoms. Both the orbitals containing the lone pair of electrons on carbon atom is p-rich, larger in size, less electronegative and more directional, while the orbital containing lone pair of electrons in oxygen atom is s-rich, smaller in size, more electronegative and less directional. Therefore, carbonyl ligand is coordinated to the metal atom in metal-carbonyl invariably through its carbon atom and through oxygen atom. The mononuclear metal-carbonyl contains only MCO linkage. Let us illustrate the nature of bonding in linear MCO linkage taking the example of chromium-carbonyl complex. This complex has octahedral shape arising from D2sp3 hybridization on chromium atom. You can see from the valence shell electronic configuration of carbon as well as chromium atom. The filled sp(z) hybrid orbital of carbon atom of carbonyl molecule overlap with the vacant D2sp3 hybrid orbital of chromium atom, forming carbonyl to chromium sigma bond. Thus, chromium-carbonyl linkage is linear. 6 such bonds are formed in chromium-carbonyl molecule. The filled 3dxy, 3dyz or 3dxz atomic orbital of chromium atom overlap with the vacant pi star, that is the pi 2px or pi 2py molecular orbital of carbonyl molecule, forming chromium to carbonyl pi bond, which is also known as back bond. chromium atom is capable of forming 3 such bonds at a time with 3 carbonyl ligands using its 3 d-pi orbitals. An average bond order equal to 1.5 is established in chromium carbonyl bond due to resonance. Carbonyl molecule is poor sigma donor, but the formation of chromium carbonyl pi bond increases the electron density on carbonyl molecule and thus increases the sigma donating ability of carbonyl molecule. Thus, the formation of metal-carbonyl pi bond is very important in determining the stability of metal-carbonyls. It not only increases the metal-carbonyl bond order, but it also strengthens the metal-carbonyl sigma bond. This type of bonding in which the two bonds reinforce each other is called synergic bonding. Any metal-carbonyl is stable only when metal-carbonyl pi bond of significant strength is formed. For example, nickel carbonyl is a stable metal carbonyl while the isoelectronic zinc carbonyl does not exist due to the inability of Zn2+ to form Zn2+ coordinate bond with carbonyl. Carbonyl pi bond on account of its dipositive charge. The metal-metal bond in binuclear and polynuclear metal carbonyls may be formed by overlapping of singly occupied hybrid orbitals or d-atomic orbitals of two metal atoms. The MM bond may be a normal sigma bond or bent sigma bond or a delta bond. In Mn2 carbonyl complex, the Mn-Mn bond is formed by the linear overlapping of singly occupied D2sp3 hybrid orbital of two manganese atom. You can see the valence shell electronic configuration for manganese atom 1, for manganese atom 2, for manganese atom forming a complex with carbonyl molecule. In cobalt carbonyl, the cobalt-cobalt bond is formed by the bent overlapping of singly occupied D2sp3 hybrid orbitals of two cobalt atoms, resulting in the formation of bent cobalt-cobalt bond. You can see from the diagram the bent overlapping of singly occupied D2sp3 hybridization. In Fe2 carbonyl complex, the Fe-Fe bond is formed by the lateral overlapping of singly occupied 3dxy atomic orbital of two Fe atoms. It is a delta bond involving 4 overlap zones. Now, let us see the nature of bonding in bridging MCO-M linkage. CO ligand has tendency to bridge two metals. In the most cases, the MM bond is accompanied with the CO bridging. The carbon atom of the bridging carbonyl group may be regarded as sp2 hybridized. The carbon atom of the bridging carbonyl molecule forms two sigma bonds with neighboring two metal atoms. This bond is formed by the overlapping of the singly occupied sp2 hybrid orbital of the carbon atom and singly occupied hybrid orbital of the metal atom. Thus, the bridging carbonyl group forms the bent linkage. The carbon-oxygen bond order in the bridging carbonyl group is almost equal to 2. In the cobalt carbonyl, the bonding in the bridging cobalt carbonyl cobalt linkage is shown in the diagram. The ability of the carbonyl group to act as bridging ligand decreases with increase in the MM internuclear distance as expected, as evident from the following examples. Let us see this table. For the metal-carbonyl complex of Fe2 carbonyl, the atomic radius of metal is 1.17 angstrom and the number of bridging carbonyl group is 3. For OS2 carbonyl complex, the atomic radius of metal is 1.26 angstrom and the number of bridging carbonyl group is 1. For Fe3 carbonyl complex, the atomic radius of metal is 1.17 angstrom and the number of bridging carbonyl group is 2. For the OS3 carbonyl complex, the atomic radius of metal is 1.26 angstrom and number of bridging carbonyl group is 0.
Let us try to understand the formation of dicobalt octacarbonyl, and for that let us consider the ground state of the cobalt atom, that is its electronic configuration. What we have is 3d7, 4s2, and 4p0. Now as this gets excited in the presence of this carbonyl ligand, this electron will come in this orbital, and as a result what we get is, so this is one of the cobalt because we have two, so let us write similarly for the other cobalt also, there will be similar status. So what happens is, between this and this there will be formation of the cobalt-cobalt bond, and this will be the bent bond that we'll see in its structure. Between this electron and this electron sharing, it will be via a carbonyl, and this carbonyl, you can notice, will be the bridging carbonyl. There will be another bridging carbonyl which will be between these two orbitals, and so you can say there are two bridging carbonyls. There will be 6 terminal carbonyls. So one gives the pair of electrons in this vacant p orbital, another will give here, another will give here. So you can see these are the 3 terminal carbonyls on one cobalt, and similarly on the second cobalt also there will be 3 carbonyls which will be acting as and getting attached as the terminal carbonyl ligands. And another thing to notice is that because of the two d orbitals, 1s and 3p orbitals, there is a d2 sp3 hybridization which is involved in the formation of dicobalt octacarbonyl. Okay, after understanding how the D2 sp3 hybridization is taking place, and let us try to draw the structure of dicobalt octacarbonyl. So these are the two cobalt atoms, and they have gone into D2 sp3 hybridization, and we have understood how there will be formation of a sigma bond between this carbonyl, let us make this orbital here, and this carbonyl, and notice that this will be a bent in shape. Furthermore, we have understood that how there will be two bridging carbonyls, that is one bridging carbonyl is as shown here and another bridging carbonyl between these two cobalt atoms. And we have also seen how the p orbitals will be involved in the formation of, after obviously via the D2 sp3 hybridization, with the 3 carbonyl ligands as terminal ones. So these are the 3 terminal carbonyl ligands with this cobalt, and similarly there will be 3 terminal carbonyl ligands with this another cobalt. So in all what we have is we have the CO2 and there are two bridging carbonyls, one sigma bond between the two cobalts, and there are 6 terminal carbonyls, and so there are total of 8 carbonyls, and this is how the structure of dicobalt octacarbonyl is. And let us look at this proper structure. As I told you, these are the two orbitals which are overlapping between the two cobalt, and this is the sigma bond formed, and notice that this is the bent bond. And furthermore we have understood that this is one carbonyl between the two cobalt, and this is the bridging carbonyl. Similarly, there is another bridging carbonyl between these two cobalts, which is here, and we have seen that these are the 3 terminal carbonyls on this cobalt, and similarly these are the 3 terminal carbonyls on this cobalt. And notice another thing here is that if you look at the plane of these two cobalts, then these two planes are also bent in relation to each other. So this is not a linear structure, rather it is an angular. You can see there is a bend and there is a angle between these two planes. Let us try to understand the structure of di-iron nonacarbonyl. And if we see the valence shell electronic configuration of iron in the ground state, what we find is that is it is 3d6, 4s2 and 4p0. Now in the excited state, that is in the formation of this molecule, one of the s electrons of 4s comes here, that is in one of the 3d orbitals, and as a result the excited state has this structure. Iron has this electronic configuration. Similarly, we can write the electronic configuration of the second iron, as there are 2 iron which are involved here. So here also it is same. Now what happens is, in the presence of these 9 carbonyls, when this how this metal carbonyl bond takes place, let us try to understand. Now you can see here that between this orbital and this orbital there will be formation of the sigma bond between the 2 iron, that is this iron and this iron. And if we see where there will be the bridging carbonyls, there will be one bridging carbonyl here, there will be another bridging carbonyl here, and there will be another bridging carbonyl here. So there will be 3 bridging carbonyls between these two iron atoms. And furthermore, these vacant orbitals, you can see now there will be 3 carbonyls which will be acting as the terminal carbonyls. So 3 are here on one iron, and similarly in these vacant orbitals there will be 3 carbonyls. So there are total of these 3 and 3, 6 terminal carbonyls, and what you can see here, these are the 3 which are between these 2 irons, and they are the bridging carbonyls. And another thing that you can notice, that if you look at the orbitals which are involved which will undergo the hybridization. You can see here that you have this D, so there are 3 Ds, 1 S and 3 P. So there are total of these orbitals which are involved on this iron, and similarly these involved in this iron which will be undergoing hybridization. So if we try to see what type of hybridization is involved, you can see there will be 2D, that is this one and this one, 1S and 3 of the P's, and that's how you are having D2sp3 hybridization, which is there in this di-iron nonacarbonyl. And this you can see here also, this is one D, another D, this S and these 3 P's which are involved in this iron, which are undergoing the D2sp3 hybridization. And now we can look at the structure and understand how we have seen the formation of bonds. So this and this, these are the 2 iron atoms, and you can see that this is the bond between the 2 iron atoms, which is the sigma bond. And then if we look at the bridging carbonyls, this and this, these are the 3 bridging carbonyls. And if we look at where are the terminal carbonyls on this iron, these are the 3 terminal carbonyls, 1, 2 and 3. And similarly, if we look at this iron, then these are the 3 terminal carbonyls. So there are total of 3 and 3, so there are 6 terminal carbonyls in this molecule.
Now let us summarize what we have learned so far. Both the carbon and oxygen atom of carbonyl molecules are sp hybridized with CO bond order 3. Carbonyl molecule has 1 electron pair on both carbon and oxygen atoms. The hybrid orbital containing the lone pair on carbon atom is p-rich, larger in size and more directional. The hybrid orbital containing the lone pair on oxygen atom is s-rich, smaller in size and less directional. CO ligand is attached to the metal atom in metal-carbonyls invariably through its carbon atom. The terminal carbonyl group has the linear MCO linkage. The bridging carbonyl group has the bent M linkage. Carbonyl is a sigma donor as well as a pi acceptor ligand. The filled sp hybrid orbital of carbonyl molecule overlap with the vacant hybrid orbital of the metal atom, forming the metal-carbonyl sigma bond.